In this video, we're going to discuss powers of a matrix. The problem is we're given this 2 by 2 matrix A, and we'd like to find the matrix A raised to the power 2015. Let's start with A squared. This means multiply A times A using usual matrix multiplication. So in other words, we'll multiply A by itself. And thinking back to matrix multiplication, normally we circle the rows of the first matrix, columns of the second matrix, and we're forming a bunch of dot products. So the product is going to look like -1, -1, 1, 0. All right, now that we've got that, let's figure out A cubed. So A cubed would be A squared times A. We figured out A squared in the previous step, so I'll copy that down. And if we multiply that by A, doing our usual matrix multiplication process now, we get -1, 0, 0, -1. So let's try if A to the fourth will be A cubed times A. At some point you can stop circling the rows and columns once this matrix multiplication starts to seem a little bit more automatic. So this product here is going to give us 0, 1, -1, -1. Now to get A to the fifth, we'll take A to the fourth times A. This time let's try it without circling the rows and columns. We'll have 1, 1, -1, and 0. And what we're ultimately looking for is a matrix or a certain power of A that equals the identity matrix. So we may need to do a few more calculations before we end up with a power that's equal to the identity. So let's try A to the sixth. A to the sixth is A to the fifth times A. So we'll recopy A to the fifth, take our original matrix A, and we'll do this multiplication. And we're going to have 1, 0, 0, and 1. Aha, so finally we have a power which is equal to the identity matrix I. So what we should do now is recap a few properties of this identity matrix, and we'll see how those properties will help us to solve the problem. So we're looking at this identity matrix here, which has 1s along the main diagonal, 0s on the off diagonal. Doesn't necessarily have to be a 2 by 2 matrix, could be a 3 by 3, 4 by 4 matrix, etc. So let's look at some properties that this identity matrix has. First property, I to the n is equal to I for any positive integer power. It's sort of obvious when the power is 1, so let's say for n equal 2, 3, etc. So again, this would be true for the 2 by 2 identity matrix, but also for 3 by 3, 4 by 4, etc. So just to convince ourselves of this, let's say, for example, if we take the 2 by 2 identity matrix and multiply it by itself, we can check that, yes, we do get back the original identity matrix. All right, second property that I has, if we take our identity matrix times any matrix B, provided that the sizes are compatible here, we're going to end up with that same matrix B. So let's say for any choice of B. And let's just do a little example to convince ourselves of this. So we take the 2 by 2 identity matrix. Let's say B is the matrix that looks like E, F, G, H, for example. If we do this multiplication, we end up with E, F, G, H. So in other words, we end up with this original matrix B that we put in here. All right, so let's see how these properties here tie in to the problem that we're trying to solve. So here's the idea. We've discovered that a to the 6 is the same thing as the identity matrix, and we know that the identity matrix has some nice properties. So the trick will be to take a to the power 2015 and to write it as a to the 6 times a to the 6, and we'll want to multiply by a to the 6 a whole bunch of times. Feel a little bit better about this if we didn't have these dots here. Just doing our usual matrix multiplication, so a to the 6 times a to the 6 whole bunch of times. And then at the end here there will be some product or some last factor. So I've just recopied our basic idea from the previous screen, and let's see how we can write out this product. So first of all, I'm going to think about what happens if I divide 2015 by 6. Using a calculator, you're going to get something like 335.83 repeating. Might be a little bit nicer to write 2015 over 6 is equal to 335 plus 0.83 repeating. And if we then go through and multiply both sides by 6, then we've got 2015 is equal to 6 times 335 plus, we'll have this remainder here. If we go 6 times this expression here, we're getting 5. So let's take this expression that we've just figured out, and let's say that a to the 2015 can be rewritten as a to the 6 times 335 plus 5. And now we're going to think about some exponent rules. So first of all, when you have a sum in the exponent, that's the same thing as having a product, so we could rewrite this as a to the 6 times 335 times a to the 5th. Okay. Now looking at the first factor, when we've got a product in the exponent, we can rewrite that as a to the 6 raised to the power 335. So whenever we've got a power raised to another power, those powers multiply. That's our second exponent rule here. And we'd still need to multiply by a to the 5th. Now, the reason why we're doing this is, remember, we said that a to the 6 is equal to the identity matrix. So we can now say this is I raised to the power 335 times a to the 5th. Using our first property about the identity matrix, when you raise it to any power, you're getting back the identity matrix. So this is really I times a to the 5th. And thinking back to the second property of the identity matrix from our previous screen, when you take I times any matrix, you just get back that original matrix. So this gives us a to the 5th. Technically, if we're being very careful about the notation here, I want to be careful about this dot. It's certainly not a dot product, so it might be more correct if we actually put brackets on here. The notation then gets a little bit more cluttered, but we're being more rigorous with the notation this way. All right, so what we've determined finally after all this calculation is that a to the power 2015 is equal to a to the 5th. You could leave your answer like this, or more specifically, you could go back to the previous screen and just copy out explicitly what a to the 5th was. It was the matrix 1, 1, negative 1, 0.